Okay, looking at question 2 of the acid-base equilibrium tutorial, we are supposed to define pH. So pH is simply negative log base 10 H plus concentration. Okay, so you can use a formula to represent the concentration, or rather the definition of pH, or you can actually also follow the definition in your lecture notes where we see that pH is defined as the negative logarithm to the base 10 of the concentration of H plus ions in solution in mole per dm cube. Okay, so this will be my preferred definition because it's easy and it's non-ambiguous. Okay, moving on next, you're supposed to calculate the molar concentration. So the word molar basically just means that you want concentration in mole per dm cube. Okay, so you're supposed to calculate the concentration of your H plus ions in apple juice, given that the pH is 3.5. So pH, as what we did earlier on, is negative log base 10 H plus. Based on your log rules, H plus will be equals to 10 to the power of minus pH. Okay, so basically this is nothing chemistry about it. It's basically a mathematical application. Alright, so if I were to show you the intermediate working, it will be negative pH equals to log base 10 H plus. Alright, then your log rules of log A, B equals to M, A to the power of M will be equals to B. Alright, so I'm just applying the same principle. Alright, so in this case, H plus equals to 10 to the power of minus pH, 10 to the power of minus 3.5. You key in your calculator. You should be able to get 3.16 times 10 to the power of minus 4. Again, remember your units. Alright, and answer to 3 SF. Okay, so that's A. Quite straightforward question. We move on to part B. Okay, part B, you're doing titration with apple juice. So this 25 cm cube sample of apple juice, this will indicate that the apple juice is actually inside the conical flask. Alright, so it's aliquot. Alright, you use a pipette to pipette 25 cm cube, and in it, what's going in is your NaOH. So the question provided some context in terms of apple juice containing a single monobasic acid. Now, what does single monobasic acid means? This word monobasic means that this acid contributes only 1 H plus per acid. Alright, 1 proton per acid. And this is typically represented as a HA. So why is this important? It's so that we know what's the mole ratio between the acid and sodium hydroxide. Alright, so in this case, because it's monobasic acid, HA will react with NaOH in a 1:1 ratio. Okay, so establishing the mole ratio is important because from the information in green, we will be able to find what is the concentration or what is the number of moles of NaOH. Okay, so applying our C times V, we can find out the number of moles of NaOH. So 2.75 times 10 to the power minus 3 moles. Okay, so this is simply your concentration multiplied by volume. Again, you need to convert cm cube to dm cube. And then therefore, for titration, exactly neutralize, this means that if there's same number of moles of HA and NaOH at this particular point, the amount of HA in 25 cm cube, because you're using 25 cm cube to do titration, you have 2.75 times 10 to the power minus 3 moles in 25 cm cube. And therefore, to calculate concentration, what we have now, this is amount, your moles, this is your volume. To find concentration is equals to N over volume. Of course, your volume needs to be converted to a dm cube. So HA will be equals to 2.75 times 10 to the power minus 3 moles. That's the number of moles divided by 25 cm cube. Convert to dm cube. You get 0.110 mole per dm cube. Alright, so that's for part B. Okay, we move on to part C. Okay, for part C, the question requires you to compare between your answer in A part 2 and part B. Alright, and to make an explanation for the difference. So let's take a look at what this question is trying to achieve here. So in A part 2, what we have calculated was the concentration of H plus. In part B, what we have calculated is the concentration of HA. Alright, so HA we calculated it's 10 to the power. HA we calculated in part B is 0.100 mole per dm cube. And H plus we calculated in earlier part in A part 2 is that 3.16 times 10 to the power minus 4 mole per dm cube. One look, you can immediately see that the concentration of HA it's a lot larger than H plus. Okay, what this means is that not all the acid has dissociated to give H plus. Alright, in fact, very little acid has dissociated to give H plus ions. This indicates that your HA must be a weak acid. Alright, which only dissociates partially to give a H plus that's much smaller than your concentration of HA. Alright. Okay, so that's your C part 1. We move on to C part 2. In C part 2, the question asks, what constants can be determined from these two results? So what have we got so far? We have the concentration of H plus. We also have the concentration of HA. What constant? So think about it. The only constant that you guys learn in this topic is your acid dissociation constant, base dissociation constant, and Kw. So you have your Ka, Kb, and Kw. These are the constants that you guys learn, equilibrium constants, right? So in this case, given that we have H plus and HA, it matches what we know about our Ka. Ka is your H plus concentration, A minus over HA. So what we can find is actually the acid dissociation constant, Ka. Okay, so we can solve this using our concept from Chem Equilibria, where we solve it using an ice table. So HA, we started off with 0.110, 0, alright, that's the concentration of HA. So what I substitute was from here, 0.110 to over here, okay? We know that equilibrium, there's going to be 3.16 times 10 to the power minus 4 mole per dm cube of H plus that was determined earlier on. And because it's a 1:1 ratio between H plus and A minus, the concentration of A minus will be the same as H plus. So the change will be a corresponding plus 3.16 times 10 to the power minus 4. The change for your HA will be corresponding a negative. Alright, just like what we do for ice table. Alright, so when your products are increased, your concentration of your reactants will decrease correspondingly. And therefore then you can find the equilibrium concentration of HA. And when you substitute in the values at equilibrium into the Ka expression, like what we mentioned just now earlier on, H plus A minus over HA, okay, we can find the Ka value. Alright, and in this case, right, you just essentially key in your calculator. Alright. Okay, so substitute into your expression and solve. Okay, in terms of the units, why do you get the units of mole per dm cube? Because you have mole per dm cube on top, raised to the power of square, right? Two concentration terms here, and one concentration term below. So you can cancel away this with that of the units on top, and that's why you end up with mole per dm cube. Now, this method is what we learn using Chem Equilibrium. Alright, but again, this method is quite laborious, as you can see. Alright, we're going to use my preferred method in this topic, which is the approximate method. Okay, so we know that since we know that HA is going to be a weak acid, we can apply our formula of, okay, again, this is for weak acid, just like what we have discussed in question 1. Weak acid H plus equals to square root C times Ka. What is C and what is Ka? C is the concentration of the acid, concentration of HA. Alright, so what we want to find is Ka. So we make K our subject. Alright, so in this case, 3.16 times 10 to the power minus 4, that's the concentration of H plus. That's what we have found early on in in A part 2. Alright, concentration C is your concentration of HA, which is 0.110 times Ka. So you can see the main difference between method 2 and the earlier method is that over here, okay, apologies for the technical difficulty. Over here, the difference is over in terms of whether I find the equilibrium concentration of HA. Now, why can I just substitute 0.110 over here? Because I assume that HA is a weak acid, and therefore the HA at equilibrium will be very similar to the HA initial. Right, because if you do actually calculate out 0.110, subtracting away 3.16 and 10 to the power minus 4, you key in your calculator, you realize that it's got a value that's very close to 0.110. So therefore, I make this assumption. Okay, and because of this, it's an approximation method, but it makes the solving a lot easier. Right, instead of having to construct ice table, I can just make use of this formula, and then therefore I can find what is my Ka. Okay, so once you have all of this, the whole idea is down to solve this mathematical expression. So for those of you who are not mathematically inclined, okay, basically we'll take square on both sides. So you end up with 3.16 times 10 to the power minus 4 square equals to 0.110 times Ka. And then we solve for Ka. Alright? So we take square on both sides to get rid of the square root. And you end up with 9.08 times 10 to the power minus 7 mole per dm cube. And in this case, alright, you can see the difference between the earlier method and that of the approximation method, alright, it's quite similar. Alright, the difference is not significant. Okay, so again, I want to highlight, in this case, I would rather you guys save time and use method 2 instead. Okay? If not, the last part is from part D. For part D, we are supposed to suggest with reasoning whether you expect the same volume of hydrogen gas to be evolved in each case. When? Alright, key thing, you use equal volumes of the monobasic acid and hydrochloric acid. Key idea is that you are using the same concentration. Okay, so the number of moles of HA, because you're using the same volume, same concentration, is the same as the number of moles of HCl. The key difference between these two acids is that HA, earlier on we discussed, it's a weak acid. HCl, it's a strong acid. So the question wants to us to discuss if we expect the same volume of hydrogen gas. So if you recall from your O-level work, acid and metal will form hydrogen gas. Alright. Key essential is that essentially you can view it as a redox reaction. Your zinc is oxidized to zinc 2 plus, H plus is then reduced to H2. Okay, so it's an acid metal displacement reaction, like things that you learn in O levels, but you also typing on essentially is H plus, the H plus ions in acid is being reduced to H2 gas, whereas the metals are then being oxidized to the metal cations. Alright, so now that we have discussed that the amount of HA is the same as number of moles of HCl because I use the same equal volume and same concentration. The question is, do you expect the same volume of hydrogen gas? Okay, so what's the main difference between a weak acid and that of a strong acid? A weak acid dissociates partially, right? Whereas a strong acid dissociates completely, alright, as you can see from the arrow. So naturally, you may have the misconception that, sure, H plus for the weak acid will be lower. True enough, the concentration of H plus will be lower than for a weak acid compared to a strong acid, alright, because HA only undergoes partial dissociation. But if you think about it, when your zinc is added, the zinc reacts with H plus. As a result, your H plus concentration decreases. For a reversible reaction, remember we say that if some concentration of a species in the equilibrium decreases, your Le Chatelet's principle kicks in. So when zinc reacts with H plus decreases. And therefore, based on Le Chatelet's principle, the equilibrium position will now shift How do I counteract this disturbance? The equilibrium position will now shift right to produce more H plus in order to increase H plus concentration. This is in line with the understanding of LCP, in which we want to counteract the change or the effect of the disturbance. But now, because the question says that zinc is in excess, so reaction 1 will then shift right until all the H plus is used up. Alright, and all the HA has fully dissociated. Okay, because zinc is in excess, so if you continuously remove H plus, equilibrium position, will keep shifting right until all the HA will fully dissociate to give all the H plus. Now for reaction 2, what happens is that because it's a irreversible reaction, all the H plus is already dissociated, so we use excess zinc, the reaction 2 will also go to completion as all the H plus will be used up. So if I look at reaction 1, a reversible reaction, and reaction 2, alright, because in this context zinc is used in excess, it doesn't matter whether is it a weak acid or strong acid. Both reactions will eventually lead to completion, right? Which means, in this case, since I use the same number of moles of HA and same number of moles of HCl, the amount of H plus, because both reactions go to completion, the amount of H plus will also be the same. The amount of H plus from weak acid and number of moles of H plus for strong acid given completion. Alright? Because zinc is in excess, all the H plus will be dissociated for both acids. So if the H plus is the same for both reaction 1 and 2, the amount of hydrogen gas that's going to be produced will be the same. The volume of hydrogen gas evolved in each case will also be the same. Okay, with that we are done with question 2.